Hey everyone, welcome back to the Rust Review. I'm Brandon Conkle, and I've been a full stack developer for more than 15 years now. I love Rust, and I really believe it'll play a big role in the future of software development. On this show, I sift through articles and topics from sources like This Week in Rust, the Rust subreddit, the Rust tag on Mastodon, Discord, fellow Rustations, and more to find interesting topics to share with you about Rust and beyond. I've really enjoyed having some downtime between projects this month, and I've been able to do some experimentation and writing that I've wanted to get to for a while now. I'll be highlighting one of my own blog posts in today's episode, reflecting on my time spent onboarding and building with Rust and with Go and comparing the two because I think they both target a specific niche. I'll also be recording some new videos soon and publishing them in the weeks ahead based on a couple of demo projects that I put together to support some additional blog posts that'll be coming out soon for Nearform. Nearform has been awesome, giving me the opportunity to spend a little bit of time between projects to experiment, to try out some ideas, to put together some good content. So be on the lookout for some blog content on the Nearform blog soon. I'll share that on my YouTube channel as well. And I'll, like I said, record some video overviews and talk through some of the things in more detail. So be on the lookout for that soon. But for now, for the immediate future, I'm going to be taking some time off, a couple of weeks starting next week, to support my wife through open heart surgery. We've been told the procedure that she's undergoing is low risk, but it's definitely going to be a tough recovery process. So thankfully, the operation should solve a problem that has posed a major heart attack risk for her. So that's a good thing. It's going to be hard to go through, but I'm looking forward to her being safe and sound on the other side and being able to let go of some worry that has been growing in recent years. So definitely going to take some time off and navigate all of that. But thankfully, there have been some interesting Rust articles over the last couple of weeks to keep my mind occupied as we are leading up to this. So I'm looking forward to talking about some of them today. In this episode, I'll talk about an engineer's dream to rewrite Rust and why they would want to. Linus's response to the kernel controversy that we talked about last time. My own blog post on choosing between Rust and Go. Google's encouraging post about memory safety's long-term effect on vulnerabilities, which was really cool to see. Reflection on Rust after a year in production. I love those posts. I love getting that real world experience and what they've learned and more. I'll kick off today's episode with rewriting Rust from Joseph. Let's see. It was Joseph Gentle. He goes by the nickname Seth. And he posted a really interesting article here on something that I think a lot of us have thought about how Rust is kind of slowing down a little bit, how the progress on the language has really slowed down, and what he would do if he had the freedom to break backwards compatibility or even just some alternative ideas. I think I like the features that he talked about, but what was more interesting to me, I think, was one of the suggestions that he made a little bit further down here about possibly compiling his own custom edition of the Rust language that would still compile all of the previous stuff that Rust has done. It would maintain compatibility with mainline Rust, but it could add a bunch of additional features, things that he's been thinking about, things that he proposes here, other things. It's an interesting article, so definitely dig into it if you're interested in some of the ways that Rust could change. I think he makes a really good point that progress has slowed down a lot, and he calls out the Rust Unstable book. So I'll pop that open really quick. This Rust Unstable book has all kinds of different compiler flags for all of these different unstable features. He counts over 700 of them that have been implemented, that are actually included and can be used, just not in stable Rust. And I think he rightly calls out this is pretty crazy that these things have gone on for so long. They've hung out for so long, and they've not been merged. They've not been enabled in stable Rust. Rust is still very slow moving, and I think that's intentional in a lot of ways. They really do want to maintain that backwards compatibility commitment, and they don't want to end up in a Python 2 versus Python 3 kind of situation, where Python 2 hung out for a long time, and Python 3, it introduced a lot of confusion, a lot of incompatibility. There was an effort to try to count off how many of the popular Python packages were updated for Python 3. Those days were tumultuous, and Rust doesn't want to go through something like that. I get that, but there's so much innovation that could be introduced into the language. And so Joseph makes the point, is this ever actually going to happen? So he calls out the coroutines RFC. It's 7 years old right now. 7 years old is a long time in software development. And he says they're implemented in the compiler. They're just not available for us stable Rust peasants to use. And I like the observation that he made. If coroutines were a child, they'd be in grade school by now. So he makes the assertion, and I think he's probably right about this, that Rust is calcifying because its consensus process just doesn't scale. And we've seen criticism about this in other posts as well, where it's taking Rust a lot of time to decide things. There's a lot of contention. There's a lot of back and forth and argument. He calls out, where is it? This particular thread. Let me pull that up on the screen. Talking about improving mutexes, and it's been hanging out for a long time. You can see it was posted on February 7th of 2022, and there's a lot of interaction here, even with diagrams and things like that. There's some pretty interesting conversation going on there. But he makes the point that 25 smart, well-meaning people spent 2 years and over 200 comments trying to figure out how to improve mutex. And as far as he can tell, in the end, they more or less gave up. That's not the sign of healthy governance. That's not the sign of healthy leadership, in my opinion. And so I think this criticism of Rust is valid. But I don't like the assertion that he makes here, that it might be time to think of Rust as a fully baked language. It's going to be what it is forever. Python 2.7 for life. He calls back to the 2 versus 3 controversy as well. And I don't like that. I want Rust to continue evolving. I want Rust to continue improving. I don't want to have something that has a time limit on it. And so the suggestion that he makes is interesting. And I'm not sure if I'm fully for it or against it, but it's an interesting idea because it harkens back to the days when JavaScript was like this, when JavaScript was very slow moving, when the browsers weren't embracing the ECMAScript, JavaScript spec improvements, and things were kind of at a standstill. And I think the approach of transpilation, the idea of Babel and other things like that could transpile upper versions, higher versions of JavaScript, ECMAScript, and things like that down to plain JavaScript. That was a really innovative solution. I feel like it allowed people to use different syntax. Some of the things that we used back then, things around like generators and things like that, they didn't always land in the language the same way they were as when we used them, but they still provided value. They provided convenience. They made it easier for us to implement features. And then later on, if we needed to go back and upgrade the version of JavaScript or something, I guess it doesn't apply like that in JavaScript. It would be upgrading the version of Rust that I'm really talking about. But in JavaScript, if we wanted to move back to more standards-based things later on something that we built with Babel or something like that, then yes, we could go back and update that code, but it should still work with the shims, the polyfills that we used and things like that. I feel like it wasn't perfect. It was definitely difficult to debug sometimes, especially when you were trying to understand how it translated back to regular browser-friendly JavaScript. But it enabled a much better workflow on top of using JavaScript in the browser, using the older version. And this sounds like something similar to me. This sounds like a way to augment Rust. You would still compile mainline Rust. You would still compile everything in the main version of Rust, all the crates on Cargo, all of those open source packages out there would still be available to you. But maybe you could add some additional features like he's talking about on top of Rust, with the understanding that they're unstable. They may change. You might have to update your project later. And so it's the kind of thing that might be good for an early stage project rather than one that's really mature. It might be something where there's a lot of early development going on. Things are changing quickly. And so you're okay with updating a feature if it didn't land in Rust the way that you thought it would ahead of time, or if it never landed in Rust and you wanted to get off of your own edition for some reason, you could just convert it down to standard Rust, and it would be harder to maintain, but this would be in that phase after the initial flurry of development has happened. And so often that code changes less often. I don't know. There's definitely a lot of pros and cons about it. There's downsides to that, certainly. Like, you don't want to have to keep maintaining your code in order for it to continue working the same way that it did before. That's a valid criticism, I think, of some of these kind of approaches where you shouldn't have to just constantly cultivate your code even when it's not changing. But at the same time, there are some rough spots of Rust, pinning, he calls out later in this article, being a big one that really does seem like it could be worked around in a custom edition or something like that, in a way that would be not too risky, not too much overhead, but would help with the developer experience and convenience. So he calls out some interesting things in this article that he would love to see. And the first one that he calls out, I get it. He wants effects, and he would implement them in Rust as function traits. But I have definitely seen the challenge of this, and I'm going to bring up a Reddit thread in just a bit to look at Josh Triplett. He's one of the Rust core contributors who gave some detailed responses to this article in the Rest thread. He's going to bring this up, but keeping track of side effects like this is hard. It's really challenging. So what he's talking about here is encoding things that the function can do, almost like permissions, into the function. And one of his use cases is to be able to provide some layer of protection for all of the dependencies that we bring into our REST projects. So he talks about how all of our little crates that we add, there's hundreds of them. It's the same kind of JavaScript criticism on we rest on the shoulder of giants. There are so many packages that we depend on that we don't really know how to jump in and troubleshoot ourselves. And it's the same with Rust. And so kind of going along with his previous section here, he talks about how encoding some of these effects, some of these things that functions can do, would not only keep track of side effects like he was talking about, but would also provide some protection against the unpredictability of the supply chain, the vulnerability that someone could insert a change in a small, seemingly innocuous library that we're including that could end up opening some kind of major security hole. And it is a serious consideration. You have to be careful that you're using popular crates that get a lot of scrutiny so that something like that couldn't really easily be injected. But he was talking about how you could use these kind of traits to mark security sensitive functions in the standard library and provide some protection against, say, some random logging library that you pulled in, all of a sudden being able to execute arbitrary code somewhere on the server that could open up a vulnerability. That's smart. But going back to the idea of side effects, I've used that kind of a system in PureScript, for example. PureScript is a way, it's a language that compiles down to JavaScript that brings some really interesting, innovative ideas from category theory and Haskell style ML language. And does it in some ways that I think even exceeds Haskell. It has coroutines in a really interesting way. And anyway, it encoded side effects in the types. And that actually made it really hard to work with in times, because you would have these nested layers of side effects encoded into the types that you had to navigate and that you had to account for everywhere. And it became really challenging to manage all of these effects and whitelist them or allow list them and make them usable in different ways. So yes, I get the goal that he's going for, reducing that supply chain risk, saying that, hey, here are the crates that I give permission to access the file system, and these other crates shouldn't, for example. Things like that are definitely interesting. I think fully going down the road of encoding side effects in the types, though, is challenging, and it doesn't bring as much value or benefit, at least from my experimentation, to really be worth it. He talks about pinning, which we've talked about in previous episodes before. It is definitely one of the most confusing and parts of Rust, and it was really a compromise. So I get that. Pin is something that definitely needs to be improved. And then I really like this idea, the idea of comp time. He talks about Zig, and he talks about a limited set of Zig code that can be executed at compile time instead of macros. And so Rust has its macro language, and it's hard to work with. Like, who is it? I just saw a post from another longtime Rust contributor that's been working with Rust, since the beginning practically. And he said that he's never really written a proc macro. He's copied a proc macro from someone else, but he's never really dug into that. And it's a whole separate problem space and a whole separate language. And it would definitely be a lot easier if we could just run Rust instead to build our macros at compile time. Let's see. Some of the other things he talks about is working with raw pointers. I thankfully haven't had a reason to work with raw pointers a lot yet, but it does get very syntax heavy. And as he calls out, the Rust compiler seems like it's punishing you for your sins of using unsafe raw pointers. But I generally like the idea of more friction around that. So that doesn't seem like a significant problem to me. But anyway, overall, very fascinating idea. The idea of augmenting Rust, of building things on top of Rust, using Rust as a core. So having your own custom editions of Rust. It might not be the best thing for, a really core, like a Linux kernel module or something like that to use. Obviously, you would want to use stable Rust as vanilla as possible for something like that. But if you're building a product in your own startup that's going to be closed source code that you and your team are maintaining, and it's not something that you're going to be sharing widely with other people, then using your own custom edition of Rust is a really interesting idea, or enabling some of those non-stable features at the very least to gain access to some of those 700 outstanding flags. I think it's interesting. I think there are pros and cons, but I like the idea a lot. Now, Josh Triplett, like I said, he's a core contributor. He's done a lot in Rust. He responded to this in the Rust subreddit and goes in detail, responding point by point to a lot of things. And basically, the big point that he wants to get across is they're not sitting around doing nothing. They're not just bike shedding. They're not just arguing over things for 7 years. They've actually made significant progress, and it's a hard problem. And I think one of the things that he doesn't specifically explicitly say here, but I think really applies, is that Rust is something new. Rust is a new type of language with its borrowing and lifetime tracking and things like that. It approaches things in ways that other languages over the last decades have not. And so it is unique in some ways, and that gives it its strength. That gives it that's what sets it apart and makes it so attractive for companies like Microsoft and Google to start incorporating it in Android and putting it in the Linux kernel, like the article that I'll talk about next. It is something that is going to continue making its way towards the Linux kernel. There's a reason for that. This is truly innovative. They really are doing something new, but I think it brings with it some challenges that people haven't seen with other languages. Other languages haven't done things in such a novel and unique way, and so they've always had prior art they can take advantage of. They have other implementations, other language communities that they can borrow from, whereas Rust does some things really differently, does some things uniquely in its own way. And so I think some of the challenges that it's trying to solve come from that. They come from the fact that nobody's ever done it this way before. And so we're going to have to find some interesting solutions to hard problems. And maybe in some of the other language communities, those hard problems were solved in different ways because of the compromises that those languages made. But Rust is dedicated to not making the compromises, because we've seen how much damage compromise has done to things like security, to things like stability. It's a complicated balancing act. And so I think the fact that Rust is moving kind of slowly and they're really hashing things out deeply and taking years to figure out the right way to approach things is a good sign that Rust is going to be around for a long time to come. I don't think it's a sign of stagnation. I don't think that Rust is dying. I think that Rust is maturing, and it's trying to mature in a way that ensures future stability, future adoption, that makes it still a worthy platform to build long term on. And that's what they're really focused on, to the detriment of the developer experience in some ways. There are some of these suggestions for how to improve Rust that would really make things a lot easier to work with, but they want to make absolutely sure that we're not introducing new compromises that take away from the core strengths, I think, that Rust has. So it's a complicated trade-off, but I, for one, am still confident in building on Rust long term. And I think ideas like custom editions of Rust are really an interesting way to work around the problem. But long term, I think Rust is going to continue to get better. It's not stuck. It's not done. We are not looking at a Python 2.7 forever kind of situation. All right, so next up, I'm going to talk about Linus's response to some of the controversy out there, the vitriol around introducing Rust to the Linux kernel. Linus himself weighed in. So in the last episode, we talked about the non-technical nonsense that the Rust kernel team was facing as they were trying to work with the Linux kernel team. And Linus paid attention and weighed in, and he's a little bit confused. He says, I'm not sure why Rust has been such a contentious area. He says, it reminds me of when I was young and people were arguing about VI versus Emacs, pirates versus ninjas. And they still are. The point there is valid, that they still are arguing about that. That has never ended. And so I don't suppose this argument of C++ versus Rust will ever truly end either. And it's been a rocky road already. Like, he pointed out that this is not new. Back in 2022, the Register, the news blog that I'm reading from here, they call it out this way. They say that some were calling the memory safety features of Rust an insult to the hard work that had gone into the kernel over the years. But in reality, if you look at the actual quote, I think it's taken out of context there. So down here, they were saying the problem isn't just conservatism among developers, but the implication that Rust is desirable simply because of its memory safety. And he said there are possibly some well-designed and written parts which have not suffered a memory safety issue in many years. So it's insulting to the people who have done that hard work to make that code memory safe to present that is the only core reason that you want to adopt Rust. It's not just because of Rust's memory safety. It's because of a lot of things that we've talked about before. How Rust makes it easier to make things memory safe, how Rust makes it harder to do the wrong thing. Those are good reasons, but Rust's memory safety alone is not the only reason. And so that's what he was responding to there. I think it was a little mischaracterized on this Register blog a bit. But despite that, Linus concluded clearly there are people who just don't like the notion of Rust and having Rust encroach on their area. And in light of this conversation that we were talking about the non-technical nonsense, he says people have even been talking about the Rust integration being a failure. And Linus says, we've been doing this for only a couple of years now, so it's way too early to even say that. And he goes on to say he doesn't think that it will be a failure, but even if it is, that's how you learn. So he sees it all as positive. I think even if the arguments are not necessarily always so, he says. And I think that's true. I think introducing Rust to the kernel has been a good thing and has shaken things up in a good way, even if the chaos in its wake is not necessarily a good thing, and the way that people have reacted to it. And I think it's exposed some really well entrenched attitudes that are not necessarily healthy around everything. And this has been good to shake people out of some of those attitudes, I think. But ultimately, he calls out why he likes Rust. I think his opinion here is really well stated. He says C is, in the end, a very simple language. It's one of the reasons he enjoys C, or that's what Linus says. Why a lot of C programmers enjoy C, even if the other side of that picture is obviously that because it's simple, it's also very easy to make mistakes, and Rust is not. So I like that perspective a lot. It's not simple, it's not easy, and that's why it's harder to make mistakes. So in my opinion, for most of the use cases I use it for, it's a worthwhile trade-off. Definitely good to hear Linus weigh in on this and provide a really well-reasoned opinion without any like firefighting at all. So he's not necessarily known for those kind of even, calm evaluations like this, but I'm really glad that he's doing that here. He's taking the time to really contemplate it, and I appreciate it. Good opinion from Linus on Rust. All right, next up, I'm going to engage in a little bit of self-promotion, but I think that the post that I was finally able to get out on our Nearform blog is a good one. I think it's worth highlighting here. So I'm going to talk about Rust versus Go, which is right for my team. The post is on our Nearform Commerce blog. I think I could have done a little bit more to format it better, and you'll see in some of my later posts, I'm providing a little more visual interest in the way that I'm laying things out. But I think the content that I have in here is good. It's presented from the experience that I built up over the last couple of years, getting up to speed with both Rust and Go, and building big things for them. I haven't built anything significant in production yet in Rust, though production is heading soon for one of my major side projects. But I have built large-scale production work in Go. And I've got some good observations, I think, from, in my opinion, obviously you can decide whether they're good or not yourself. Your mileage may vary, but this is kind of observations I've made watching my team get up to speed with Go, and then also watching my colleagues and I get up to speed with Rust, and comparing and contrasting them. I think Go is actually a really powerful language. I think Go is a good, solid choice, even though I'm always talking about the safety and strictness and stability of Rust. It's not always a good fit. There are a lot of use cases, I think, that Go can meet better. And in fact, even though I've been very much a JavaScript and TypeScript devotee for much of my career, I'm coming around to the point where I think I might actually use Go instead of TypeScript in a lot of contexts, especially for server-side development in something where I'm intending to deploy to a serverless platform like Lambda or something like that. the packaging of JavaScript and TypeScript is still challenging in those kind of environments. And the way that Go and Rust both compile down to binary files that are statically linked, I think really is a big advantage, especially in those kind of environments. So in any case, I'll go over my article here and talk about the main points on it. I've talked about how there's been a movement, there's been a shift away from really loose, really dynamic, high-level programming languages back towards statically typed languages with low-level operating system access. And there's a good reason for it, as we're trying to scale things more and more and trying to do more ambitious things with our code, especially in the world of like AI and machine learning training and things like that. We've seen static typing start to really reemerge in languages like JavaScript and PHP and Python, adding more type checking features. I think JavaScript most prominently with TypeScript, but PHP and Python do actually have some good typing tools in their standard libraries now. I've been using the Python one recently, and it feels a little bit like early days of TypeScript with not everything actually having types, but it's definitely still really helpful, just like TypeScript was back then. So so anyway, going into high performance statically typed low level solutions, they're not all created equal. C and C++ is traditionally the choice for high performance low level programming, and it's really enjoyed dominance for decades. But there have been increasing concerns around it, especially with the memory safety. But that's not the only one. I think the comment previously is a valid one, that it's not all about memory safety, but that's definitely a big part of this. And the Google article I'll share in a bit reinforces that. But it is definitely a big concern. And if we want to continue to have this kind of low level performance, we're going to have to do a lot more to provide memory safety. And Go and Rust are two, I think, two languages that embody this, that are memory safe, but also provide low level performance and compile down to binary formats. They provide excellent performance while making it easier for developers to work with them. And I think they both can fit into the same niche of trying to move forward with better performance and better stability and better security on our applications that we deploy on servers. So I go a little bit into just high level Go versus Rust. Go's been around longer. It's generally seen as easier to use. It has a really well-designed channel-based concurrency system. So using green threads, so software threads. It's not hardware threads like Rust is. But the event loop and the model that it uses is very performant and very easy to work with. But there are definitely some quirks that require some experience really to understand, especially with how it manages pointers. Rust competes in that same space. I've talked a lot about how the zero cost abstractions, the memory layouts that help it avoid garbage collection, all of that is a really great advantage to help keep its runtime really small, help keep the binary sizes really small. But also it has a concurrency system that uses hardware threads, but still provides really strong protection against shared memory problems, enforcing synchronization and things like that in some ways that the Go doesn't, and Go has some pitfalls because of. So I've split the article up into three major phases. There's the onboarding phase, where you're trying to get new team members up to speed with the language, the architecture, the framework that you've put together for your project. And I think Go really shines here. Go is easy to learn, though it is difficult to master. I think you can get up and running and write code really quickly, but some of the conventions are unusual. It intentionally kind of bucks convention, I think, and does some things differently because it brought some convenience, and it kind of showed how it wanted to contrast itself against the current options that were available at the time. It wanted to be a bastion of simplicity and kind of fight against some of the complexity that has continued to grow around it, I think. I think their Go routines and their channels are a huge advantage in Go. This is one thing that I've been plagued by for a long time. The idea of function compatibility between async and non-async. And so I reference this, what color is your function, red versus blue functions, talking about async versus async and how difficult it is to kind of navigate the idea of where you can use them, where you can't use them, things like that. And so Go has implemented an async approach that completely eliminates that problem. You don't need async await or syntactic sugar to make this usable. It looks a lot like ifs in JavaScript, the immediately invoked function expressions, and generally the communication via channels and avoiding shared memory is a big advantage here. And it works well and it performs well. I think one of the downsides in Go that will trip up a lot of people who are used to more complicated type systems. So if you're coming from Python, you won't care. Well, no, I'm wrong. Actually, Python does have multiple inheritance, so you will care. If you're coming from a language that doesn't use a lot of inheritance, like JavaScript, maybe you won't care. But if you're coming from C#, .NET, if you're coming from Python, I think this will throw you for a loop where there is no inheritance in Go. There is no extending interfaces in Go, but they do provide a really good way to compose interfaces together, to embed an interface in another interface in a way that makes it really easy to work with and translates to JavaScript or JSON well when you're serializing. So no more ravioli code. Rust obviously is more complex. It takes more time to learn. But there are really strong benefits there. There's data is immutable by default compared to Go, where it's really not possible to make something immutable, which really provides some challenges when it comes to avoiding accidental mutation. Rust's compiler keeps track of whether a pointer is alive, whether it's mutable or not, what function currently owns the value, as opposed to Go, where you can commonly run into a null pointer exception or a nil pointer dereference, as it's called in Go. That definitely comes up a lot. I think the traits take a little bit of time, and the abstractions that you can build with Go get pretty messy at times, but they give you a lot of confidence once you can get them to compile, because the compiler does so much to prevent you from shooting yourself in the foot. I won't go in detail. This is a pretty dense article. There's a lot of stuff to pull out of here, a lot of stuff that have kind of come from my notes over the years. But overall, it really talks about how Go is focused on getting out of your way, letting you do what you want, whereas Rust is really focused on preventing you from shooting yourself in the foot and providing a lot of guardrails. So they both compile to the same kind of statically linked binary, but they both also dynamically link to libc. And so that provides, or that comes with some implications and trade-offs when it comes to embedded or bare metal kind of deployment. So you'll have to find solutions around the libc linking. I think there's a lot more support for that in the Rust community than there is in the Go community, though. I think it's possible in both. And there's definitely talking about the maintenance phase, talking about when your application's in production, you're trying to solve bugs, you're trying to keep everything running smoothly. This is where Go really has some trouble. I feel like I kept discovering gotchas along with my team, things that were quietly failing. They appeared to be working smoothly at first glance, but hid subtle bugs that disrupted production behavior. I think the fact that NPEs and accidental mutation are so easy to run across, it's almost like JavaScript in that regard, which is surprising to me for a static language like this. There's some complexity where you're really not sure whether a value is passed by reference or passed by value. The compiler kind of makes a decision at runtime about why. A really big one for me, a big pitfall, was Go's empty zero values. It automatically initializes things at a default zero value. And so if it's a number, it'll automatically initialize as 0. If it's a string, it'll automatically initialize as an empty string. And so that makes it really hard to deal with concepts like null versus undefined. Was it provided, or was it completely absent? Was it explicitly set to null, or was it simply missing? Things like that are hard to represent in Go, and serializing with null versus undefined is a particular challenge in Go. That led to some real trouble implementing patch requests on my HTTP APIs. That was something that took us quite a while to figure out a reliable way to work around. So over time, what I'm finding is that my confidence level with Go has decreased. And so I've adapted by being really defensive, always being on the lookout in code review for unintended consequences, or things that might accidentally fail, or things that might get a type of input that you wouldn't have thought before. Things like that are really important to pay attention to, just like they are in JavaScript. And so that's a downside, I think, compared to Rust, where overall I get more and more confident in my code working the more I understand what's happening. The more I understand the compiler errors, the more I learn what to do to avoid them, the more confident I get in Rust, and the more confident I get in my code. And working with Rust long term really does, like other people have said, like the interview that I covered last time, I think said, it makes me a better programmer in general, with better awareness of memory management that is largely obscured or hidden away in other languages, and are still really important. You still need to learn these things. It's just hidden away much more in other languages than it is in Rust. I think Rust has really good advantage in package management and dependency management too, and build tooling. One of the things that Rust really surprised me, or I'm sorry, one of the things that really surprised me about Go is that I can't even define dev dependencies. Go's package manager is so limited. I can't put dev only dependencies in. I have to carefully document them in my README file. So each new engineer goes to install them one by one when they're onboarding. And that was frustrating. That was something that really surprised me. So Rust's package management is definitely an advantage here. So anyway, I wrap things up with a what should I choose section that kind of analyzes different scenarios and what considerations would go into whether your team is choosing Rust or Go. So is your team used to dynamic languages with simple type systems? Are they using plain JavaScript or Python and not TypeScript or not C#? Are they using languages that abstract away memory management and rely on garbage collection? Those kind of things are a reason to lean towards Go, and you'll have to make sure that you have comprehensive test coverage to kind of make up for the looseness of Go, just like you would in JavaScript. But that's going to be a better fit for your team than trying to learn complicated type systems and category theory and things that they're not familiar with and haven't used in other languages. On the other hand, if your team has a good tolerance, if they're doing like TypeScript type level programming to transform types, and if they're creating sophisticated abstractions and they're comfortable learning about memory layouts and stack versus heap and things like that, they're really going to appreciate what Rust provides. They're going to love how Rust kind of forces you into good behavior so that you get those easy performance wins, like I'm calling out in the blog post. Or is your use case something that requires a high level of precision and performance, or is very resource constrained? That definitely points towards Rust. But if you need to rapidly iterate and experiment with different approaches, and you don't want to have to solve a lot of edge cases or type errors or things like that, which Rust, you definitely do. Rust has a level of completeness that Go doesn't have, and it won't let you run things that have a potential problem. So you have to dive in and solve those major type errors or complicated edge cases up front before it can run. And that's an advantage. I think that's a good thing. You learn over time how to avoid those things ahead of time so that you don't even get into those messes. One big consideration, though, Go has been around a lot longer. It enjoys a much wider talent pool. There are more Go developers available, although they may not always be the expert developers. And I would not put myself in this category, but the expert low-level developers that understand all of the intricacies of Go and the trade-offs of how to use it effectively while avoiding some of the major pitfalls. I think I have made some significant progress towards being one of those people that understands Go at a really deep level. But I'm not quite there yet, and I think it would take me a little while to get there. And that's a problem with Go. Easy to learn, difficult to master. But you'll have a talent pool that's easier to find. It's easier to find people to hire if you build a framework that is really uses abstractions well in a way that constrains behavior and to avoid common pitfalls in a lot of cases. Then I think that it's great. Like you can keep even people with less experience in Go in line if you're careful on code reviews and you have good abstractions that kind of constrain behavior in ways that prevent those problems. But it's definitely a challenge in Go. You have to understand that a lot of testing is necessary because you're going to be solving a lot of little fiddly things in staging and production. Whereas Rust is not the same way. Rust, it takes you longer to get code that compiles. You will often spend a lot more time tackling those edge cases and having a more complete refactor before it can ever compile and run. But in a lot of cases, once you get to that point, once it compiles, it does run and it works. And there might be some fiddly serialization things or IO things that you need to figure out. But for the most part, your Rust code itself, the core will work. And that's really a huge benefit. I think Rust developers, though, are more expensive. There are fewer of them out there. They take a lot more training and a lot more, I think, effort to get up to speed on. And so it's harder to find good Rust developers. And that means that you're going to pay more for them. And that might be a pretty significant factor. I think if you have really tight timelines and you have not the biggest budget for really expert talent, and you're trying to accomplish something on a really tight deadline or something like that, where you don't have a lot of time to tackle those edge cases, and those you probably won't reach them, but maybe errors, then Go is definitely a better choice. Go is going to allow you to be more agile to work around those things, whereas Rust slows you down on purpose for a good reason, but it does slow you down. And so that's something to think through. All right. So I tried to break this post down as much as I could. I skipped over a lot, so definitely read through the whole post. It's dense. There's a lot of information packed into each paragraph. But if you need help making that choice, if you want some help analyzing your use case, your project, the goals that you have for how your users will engage with it, if you want to decide whether Rust versus Go or TypeScript or anything else is the right way to go, and if you want help building that foundation, creating the framework that everyone can work within that prevents problems and helps enable people to tackle big features quickly, if you want help building that foundation, we here at Nearform are ready. We've been studying Rust for a while. I definitely have spread some of my Rust evangelism to other people in the team. And so there's a lot of us who have done some pretty cool things with Rust, not only in primarily Rust projects, but also embedding it into Node and TypeScript and things like that, using it in build tools. We can definitely help you. So reach out and I'll let you know how we can get things started. All right, so I've spent a lot of time on my first few posts, so I'm going to speed things up a little bit for the remaining posts. The next one that I've got up here is the Bevy Foundation, and I think this is a pretty cool change. Back in, back in March, they announced the Bevy Foundation, and they applied for 501c3 status because it would give that tax-exempt status in the U.S. and it would make donations tax deductible and introduce some stricter constraints, some stricter auditing requirements that I think really increase confidence, that will give more people the confidence to donate and to help support it and to use it. I think it's an important change, and it's really exciting that it has been granted, and the Bevy Foundation is now a 501c3 public charity. They talk about some of the benefits of this. They talk about how it buys more public trust. And they also talk about how they are able to qualify for every.org now, which is a donation platform that is much less expensive than other platforms because only 501c3s are eligible. And so there's a lot less risk, so they can provide a lot less fees and costs over the top. So it takes a lot to get approved as a 501c3. So congratulations to Bevy for hitting that milestone, and I really hope that it leads to more innovation in the future. I've seen some things come out from Bevy recently. People are really using it for really cool production implementations. I saw someone introduce or release a terrarium style game on Steam the other day that was entirely done with Bevy, that uses procedural generation to help you build these really cool like atmospheres. I don't know. It's really cool. Bevy can do some pretty cool things. So definitely check it out, and congratulations to them for their new status. The next post, I'm going to try not to spend too much time on it, but definitely find it and read it. I think the Google Android team has been doing some pretty cool things, and for a while, they've asserted that their shift towards memory safe languages, not just Rust, but things like Kotlin and other languages that are not C++, they've been emphasizing this approach for years now, and they've really been pushing this as the solution to the memory safety vulnerabilities that plague the industry as a whole. There's something like 70% of all security vulnerabilities are related to memory safety. And so they look at how this emphasis in Android over the last 6 years has changed things, and it's dramatic. They say the percentage of memory safety vulnerabilities in Android have dropped from 76% down to 24% over 6 years. That's huge. That is an enormous shift in vulnerabilities, in reducing those type of vulnerabilities. And so clearly their approach worked. But they call out in the blog that this is somewhat surprising. This is a little bit counterintuitive, because the amount of memory unsafe code in Android has not gone down. In fact, it has continued to grow. And the difference is new code is memory safe. So the new code being introduced is generally the memory safe code, and the unsafe code is the old code that is still in the code base, still being used. And that therein lies the difference. In their analysis, they did some simulations, they did some graphing here to illustrate what they learned, but they found that that's the difference, that even though the memory unsafe code was slightly growing over time, the ratio of new code was heavily weighted towards memory safe code, and that actually is what made a huge difference. They looked at the memory safe vulnerabilities and kind of extrapolated and simulated it out further, and it should continue to go down. But why? They say this reduction might seem paradoxical. How is this possible when the quantity of new memory unsafe code actually grew a little bit? And they're saying it's because the vast majority of vulnerabilities reside in new or recently modified code. And this definitely lines up with my experience too. When something breaks in production, you immediately go to look for recent changes, because it's not the code that's been working in production for a while that typically has the most problems. It's typically something new, or something that recently changed or was updated or refactored or something like that. And so that new code has the greatest risk. And so if you're writing all of your new code in the memory safe language, you're addressing that risk and allowing the unsafe code to continue to age and mature, which generally leads to better safety with it as well. And so they took that, they looked at it in the real world on Android, and confirmed that it is playing out exactly the way that this data suggests, that they're seeing a large and continued decline in memory safety vulnerabilities, even though they're not reducing the amount of unsafe code in use in the code base. They're just weighting heavily or preferring heavily memory safe code for new code or changes. And so it has really played out. The number of memory safety vulnerabilities has continued to go down, and I think it will continue to go down. And as Google calls out in this blog post here, hackers are endlessly creative. And so I assume that we will move on to the next major category of risks, but it won't be memory safety. We will have thoroughly squashed that. And Google, I think they're right in calling out that this is going to slow things down significantly when it comes to the hacking front. I think that yes, they will move on to new and innovative things, but it's going to take them a long time to do that, and it's going to be a lot harder for them to accomplish it, and they're not going to be able to crank things out as quickly as they have been, and that's a huge win. So their conclusion is we don't need to throw away or rewrite all of our existing memory unsafe code. The big focus should be on making interoperability safe and convenient, and they're doing more to help with that. They're trying to push C++ interoperability with Rust to make this easier and easier to accomplish, so that you can have blended code bases without all of the pain that typically involves. So I like it. They summarize the concept by saying, once we turn off the tap of new vulnerabilities, they decrease exponentially, making all of our code safer. I love it. All right, next up, I'll move on to WebAssembly. This is something that I recently experimented with in my time between projects, like I was talking about. And this is an interesting thing that I didn't know about WebAssembly and about compiling for it. Fascinating for me to go through this. I don't think it affects anything. So one thing to keep in mind, this really doesn't mean anything's changing, but it does help me understand a little bit more about LLVM, how it interacts with WebAssembly. In my experimentation earlier, I had a hard time building to WebAssembly. I was able to use NappyRS and target the Node API for the kind of compiling that I was trying to do to include something in a Node API. A whole lot easier than I was able to target WASM. And so one of the things that it's talking about here, how WASM is changing, how the compiler is improving continually, is a really good thing to me, because I have confidence that it will get better in the future, especially with the people like shuttle.rs trying to push it forward and things like that. I think WASM is going to be a really viable target, and the portability of it is amazing. The fact that you don't have to have a Mac version and a Windows version and a Linux version and an ARM version and an M3 or an Apple M1 version or whatever. you don't need all that. You can compile it once and run it everywhere, and that's amazing. That's an awesome feature, but it's hard to build to right now. And this blog post talks about how changes are happening, how flags are for a long time optional, and then eventually many of those flags get turned on by default. And so this blog post talks about some of the things that are being turned on by default in version 19 of LLVM, and how they won't necessarily impact people who are building to WebAssembly, except in some unique cases, but they do indicate some features that we'll be able to take advantage of later once LLVM is updated to take advantage of it, and then Rust by turn is updated also to take advantage of it. So it's changes that are coming in the future that look pretty exciting. I think things are going to be possible. Things like referencing other language ecosystems, types in memory within the WebAssembly system, that will make that portability across platform and across language ecosystem even better, I think, which is really cool. Next up, Dimitri K posted on the Yield Code on his Yield Code blog about using Rust in production for a full year and some of his observations coming away from that. And I thought this was a great post. I love hearing people's experiences in the wild. I love hearing what it's actually like using these principles long term to keep a project running and to keep things moving and changing the way that they need to. And this was more reinforcement, I think, that it's a good choice. Even though there are trade-offs, it can be a good choice in production. And one of the things he called out was a huge change that he recently made. He shows the git diff stats here, and it's a big merge request. And so he says that he's been working with Rust in production for just about 11 months now, almost a year now. And even making a huge refactor like this worked surprisingly well. He talks about how most of the time, I identify with this. I do this too. He'll work on a big chunk of a refactor, and he'll do a ton of changes or feature implementation or whatever. He'll make a bunch of changes and align a bunch of things up before he ever tries to run it. And that's very different from the way that I approach development in Go or TypeScript, for example. With TypeScript and Go, I'm running them repeatedly, iterating in small chunks, little by little, seeing, okay, what does it do with that? How does it handle that? What do I get back with this? With Rust, I haven't had to do that. The type system ensures I know exactly what I get back. I think it's not necessarily like this at the beginning, greenfield. If you're building something from scratch, you're going to be iterating too. But if you're refactoring, if you're changing something that was already working, then that I find myself doing the entire refactor all at once and not iterating in small chunks, not running it over and over again and making little changes here. I'll make the big change all at once. It'll affect multiple packages, maybe, or multiple crates. But then at the end, everything generally works. He says, let's see, after setting up every component of the system and issuing a first request, I was surprised to see that everything works. And he pats himself on the back a little bit. He says, I know that I'm a good developer, but I don't fool myself that I can write code without mistakes. Nobody can. Everyone is human. And so the fact that all of this worked so flawlessly first try is amazing, and it's a testament to what Rust does for you. He said there were some minor issues with the dynamic aspects of the code, like serialization and deserialization, which is one of those areas that is a little bit unpredictable. That's where you're taking stuff outside of Rust and bringing it in. And so, that's that IO boundary. That's likely where things are most likely to go wrong in Rust. But the actual core logic just worked. And that's really similar to my own experience also. So one of the things he calls out, and one of the main reasons they use Rust at his main job, is because they had a TypeScript backend. They had a really big TypeScript backend that became unmanageable over time. And what he realized is, sure, you can hold the context of a small application in your head, but at some point it's going to outgrow your memory. At some point, the complexity of the application will grow beyond what you can hold in your head. And this was the same argument that we made a decade ago about CSS, whereas every CSS file or every CSS page, every page that was styled with CSS was essentially a big bundle of global state that you had to reason about. Everything that you were changing affected the global styling state. And so you had to keep all of the CSS, all of the styling approaches, all of the compromises, everything in your head so that you wouldn't accidentally stumble across it somewhere else. When you were working on a different part of the code and you changed a style to solve a problem, you might be breaking 5 other things. And that was the issue with how CSS worked, how everything, you had to keep it all in your head, because CSS wouldn't tell you if a change you made in one place was breaking something somewhere else. And part of that is inherently working with visual styling. It's hard. It's not as deterministic as hard logic and numbers is. But a big part of that we solved back in those days by splitting the CSS up and using tools in our Webpack workflow to set up CSS that had its own scope, that it was isolated, and you didn't have to think about the global context of it. You could just think about what you were changing for your particular component. And that it's not necessarily the same thing, because really what that's about is isolating state and separating it out into its own buckets. But with Rust, it's more about using the compiler to keep track of things that you can't, using the statically deterministic type system to help you keep track of all these things, help you keep track of the behavior that you want to encode, without having to remember everything. And so that is a big advantage of Rust, I think. He talks about, let's see. Oh, yep. I don't really remember that part, but he talked about Open API and Swagger. But I've definitely had some of the same problems he's talking about here, where third-party providers don't necessarily follow their Swagger spec. But with Rust, I think there are good ways, just like there are in other languages, to generate the Open API spec from your code so that it is reliable. So I think, sadly, the cases where you're not following your spec could be easily avoided by using tools that your language ecosystem provides. But generally, he talks about how the promise really holds out. When it runs, it really is stable, unless you're specifically doing things to circumvent that by like using unwrap everywhere or using unsafe code. But generally, it's stable, it's reliable, and it doesn't change a lot. So this is actually the other side of the coin, talking about the rewriting Rust post that we looked at first. Yes, Rust is really slow to change, but this blog post calls out why that's an advantage sometimes. I've had this same experience. Every time I sit down to create a new TypeScript project, something else changes. I just recently put together my latest Node TypeScript boilerplate, and I made the exact same change that he's talking about. Oh, don't use TS Node anymore. Now it's TSX. Things like that. It's constantly, rapidly changing, and I don't totally always see the reason for it. Like, why not make TS Node better instead of creating a separate tool? It's the classic conundrum, I guess. But then at the same time, Rust is a new tool, so why did we create something new instead of making something better? It's a catch-22. But with TypeScript, I think compared to other language ecosystems, it is rapidly, frequently changing, and you don't always see the benefit or the value in those changes. There are some things that were working well, and it seems like there's change just for change's sake. And I know that's not true. I know there are reasons that things are evolving so rapidly, but I don't know that it's necessary. And with Rust, they have made the decision to completely go in the other direction and make it actually pretty hard to change Rust. And that's okay, because it does slow things down and prevent that kind of chaotic, fast-paced change environment. And it's a good thing for projects that need to be reliable long term. I think there's a difference between a Rust API and a TypeScript API long term. The TypeScript API is going to be deprecated and need to be updated far sooner than the Rust API will. But he calls out that compile time is definitely a downside. And this is something I have personally ignored somewhat, because I've seen really big build pipelines, even with TypeScript and JavaScript. And I've seen pipelines that take 20, 40 minutes to run. So this doesn't seem like it's that big of an issue. But when you compare it with Go, it definitely is. Go has a lightning fast compile time. Go builds are generally very quick. So it is definitely a comparison. Now, he pointed out that they may have actually been missing the cache key and not taking advantage of, I'm guessing, Circle CI or something like that. That probably could speed up those compile times quite a bit by using incremental builds with previous artifacts, which is the solution that I often reached for in TypeScript to do the same thing. So yes, I think this reflection on a year of Rust in production definitely goes a long way to reinforce the things that Rust evangelists have been saying for a long time, and showing that they really are true. It really does lead to a different kind of experience in production, and that has some pros and cons, but I think the pros win out. All right, so my last topic will be a YouTube video, and this is let me mute that just to make sure. This video is one that I think does a great job of talking about the emerging space of AI and machine learning in Rust. And so this is a post from the Code to the Moon YouTube account. He's got a presence on social media under Code to the Moon. I believe his name is Ken. He talks about some of the Rust AI training tools that are out there and focuses specifically on one called Colossum, which is really interesting. It reminds me, or seems really similar to me, to transformers in the Python LLM or machine learning ecosystem, and talks about how easy it is to do some really common workflows in Colossum in Rust and sidestep the Python world entirely. And I think this is really worthwhile. I will say that I have done some recent work on Python and trying to um, embed Python into a Node API. So let's say you've got a TypeScript API that's really large. You want to add an AI feature to it. And so you've got this model that you've trained with transformers in Python. How do you use it in Node? It is surprisingly difficult. I tried a number of solutions to embed Python in Node, and none of them worked reliably. None of them scaled to the level where a load tester like AutoCannon was effectively able to evaluate it. And even reaching for things like the Python Node API bindings or things like that, that still was unstable, and I wasn't able to get it working. And so reaching for Rust and using the Rust wrappers around the Torch C++ core API, I was able to implement a solution that embedded in Node smoothly without any of the downsides, without any of the challenges of trying to embed Python in Node. The Rust and Node interoperability was smooth, easy. It was able to handle heavy load under something like AutoCannon easily. And so I think there's a lot of reasoning for looking towards Rust, especially on the querying side when you want to use it. But I think frameworks like Burn, as he calls out in this diagram here, are just part of a growing ecosystem of tools that allow you to do the whole thing in Rust. And I think he accurately calls out the fact that performance is not going to be dramatically better because most of the Python libraries use C++ libraries under the scenes. But I contend that the developer experience is vastly better. It's so much easier to understand what a Rust package can do compared to a Python package. There's so much that is just any or undefined in Python that you have to go digging in the source code to actually understand if the documentation doesn't explicitly call it out. Whereas Rust's static typing and really detailed type system makes that a lot easier to navigate. So I think there's a lot of benefits for it. And I didn't realize how many tools had grown out. I've been using the Burn framework for a little while, but there's also, as he calls out, where it's you zoom in, he does zoom in, but I can't get it to show on here. Oh, well, but he talks about Mistral.rs and Colossum, some ones that I hadn't seen before. And yeah, oh, well, I can't get a good screenshot on here, but Colossum sounds like an interesting tool that's really similar to transformers. And Mistral sounds like a great way to work with large language models. And there's definitely some really cool stuff emerging in Rust for LLM and for AI. And I think that AI is proving that it's not a fad. It is expanding and getting better. And I think Rust is a great future for it. I think Python has a lot of limitations that Rust makes a whole lot better in terms of developer experience and stability and reliability. Even if performance is not a factor, I think all of those other things are. Check out Code to the Moon for that great overview. All right. Well, I think I've spent enough time rambling on about things. I'm going to wrap things up here. If you have an article or a topic or a video or something that you would like me to take a look at and share on Rust Review, you can let me know. I'm typically hanging around the Discord Rust communities as bconkle. So you can reach out to me there, or you can find me on Mastodon. I'm on fosstodon.org/bconkle. And yeah, I'd love to hear from you. I'd love to find out if you've got a cool project that I could jump into. And I'd love to hear more about what people are working on in Rust and what kind of things are making it out into production. I think it's always great to hear about how people are doing things in the real world, and so that we don't just stay in this little hypothetical space everywhere. So thanks a lot for listening. Thanks for watching, and I hope you have a great day.